Lecture problem 5. In a ballistic pendulum experiment, a bullet of mass equals 0.060 kilograms is fired horizontally into a wooden block of mass equal 0.200 kilograms. The wooden block is suspended from the ceiling by a long string as shown in the figure. The collision is completely inelastic, and after impact, the bullet plus pendulum move together until the center of mass of the system rises 0.120 meters above its initial position. Calculate the velocity of the bullet plus wooden block just after impact and the velocity of the bullet just before impact. In exam questions like this one would be limited to part B only, but here, because that's a lecture problem, we are showing you the intermediate steps, which is part A. This question is a multiple concept question. There is a collision between the bullet and the block, and immediately after that, the new system is going to swing in the form of a pendulum. In order to solve for the velocity of the block-bullet system using the collision, and the conservation of momentum for that matter, you need to know the velocity of the bullet. Unfortunately, the velocity of the bullet is not given. Therefore, to be able to solve for the velocity of the block-bullet system, you need to use the second part, which is the pendulum. Notice in the second part of the system, the block-bullet system is going to move from one point to another. And the best concept that you should use to be able to solve questions for objects that move from one point to another is the concept of energy. First, notice that the final velocity after the collision, that's the same velocity that the pendulum is using to start swinging to its highest point. The two forces that are acting on the mass while it's swinging are the weight mg and the tension T in the string. Notice that this mass m that I am using in the diagram is representing the mass of the block bullet system, which is m1 plus m2. The weight mg is a conservative force. However, the tension T is a non-conservative force. But in pendulums, the tensions always act in a perpendicular form with the velocity of the block. Therefore, the work that is done by the tension is always going to equal 0. Conclusion: the work done by the non-conservative forces must equal 0 also. For that reason, it is possible to use the conservation of energy principle, where the kinetic energy initial plus the potential energy initial is equal to the kinetic energy final plus the potential energy final. The initial point is going to be chosen where the mass is located at its lowest point, and the final point is that one where the mass is located at its highest point. Therefore, the kinetic energy at the bottom is 1/2 times the mass of the block bullet system, which is m1 plus m2, times the velocity initial squared. The gravitational potential energy is equal to m1 plus m2 times gravity times the height initial. The kinetic energy final is 1/2 times m1 plus m2 times the velocity final squared plus the potential energy final, which is m1 plus m2 times gravity times the height final. The reference point of measurements for the heights is going to be the lowest possible point. Therefore, the initial potential energy is going to be equal to 0. Since the block bullet system is going to have 0 velocity at its highest point, therefore the kinetic energy at the highest point is also going to equal 0. Notice also that the m1 plus m2 is a common factor, therefore it cancels out. As a result, this expression can be simplified to be 1/2 V initial squared equals G H final. Multiply both sides of the equation by 2, you end up with V initial squared equal 2 times GH final. If you square both ends of the equation, you end up with V initial equal the square root of 2 times GH final. Solving for the VI, we obtain 1.53 meters per second. Now, to be able to solve for the velocity of the bullet, we need to go back to the collision, where the bullet collided with the block. In order to check if the momentum is conserved, we need to look if the net force is equal to 0. The block is under two forces, the weight m2g and the tension. And those two forces clearly cancel each other out. The bullet, however, is under single force m1g only. And clearly that force is not cancelled by anything. Technically speaking, the net force on my entire system is not equal 0, and therefore the momentum is not going to be conserved. However, notice that along the horizontal axis, the net force is equal to 0. As a result, we can only apply the conservation of momentum along the horizontal, because along the horizontal, the net force is equal to 0. Along the vertical, the momentum is not conserved. The momentum before the collision equals the momentum after the collision. Before the collision, the momentum comes from the bullet, which has a mass m1 times its velocity v1, plus the momentum of the block m2 times v2. After the collision, the bullet becomes embedded within the block, therefore I have one single object, m1 plus m2, times the final velocity. Notice that this final velocity, which is the velocity of the block bullet system after impact, is the same as the initial velocity of the pendulum. Break this equation into components, and we have only x component here. The m1 v1 is pointing towards the positive, which is the right direction. The m2 v2 is equal to 0 because the object is initially at rest. After the collision, the block bullet system are going to move in the positive direction, therefore m1 plus m2 times v final. Isolating the v1, which is the velocity of the bullet, you obtain m1 plus m2 times the final velocity divided by the mass of the bullet. Notice one more time that this final velocity here is the same as the one that I solved for before, which is 1.53 meters per second. Solving for the velocity of the bullet, we obtain 6.63 meters per second.